Hello, everyone. So this is a continuation of the lecture on Khovanov-Rozansky homology of torus links. Part one focused on this technique for computing Khovanov-Rozansky homology, or at least some approach to the computation of Khovanov-Rozansky homology. And this video, part two, will be its application to torus links. So I want to emphasize we will only say anything about positive torus links. There's actually an important difference between positive and negative torus links, or in general between the Khovanov-Rozansky homology of a link and its mirror image. This may come as a surprise to, or it may sound kind of strange to people who are unfamiliar with this purificated version of Khovanov-Rozansky homology, but keep in mind these homologies of links are typically infinite dimensional vector spaces. They're like finite in each degree, but finite dimensional in each degree, but there's infinitely many degrees to worry about. And so usually you would expect something like taking the mirror image of a link dualizes the complex representing that link. So that like the complex that computes homology of this link and complex that computes the homology of its mirror are dual to one another in one sense, is usually what you would expect. But the sense in which they're dual is they're not dual as complexes of vector spaces. They're dual as like modules over a big ring. Anyway, so when you take duals, you have to worry about the module structure over this ring and so on. It's quite a bit more complicated than you would expect. So we'll stick to positive torus things here. A bit of history about what was computed before. So in 2015, me and Ben Elias computed the Khovanov-Rozansky homology of the NN torus link. But for us, this was a kind of a case study. We introduced this technique for computing things, and we applied it to this example both as like a case study, but also this was particularly important for our categorical diagonalization story. I extended ideas to like some more families of torus links in 2017. Essentially at the same time, Anton Mellet computed the Khovanov-Rozansky homology of torus knots. So that is the case when n and m are coprime. And then, so it turns out Mellet's idea generalizes to positive torus links, not just knots. So this will be the focus of today's talk, this paper. So it includes the previous computations as special cases. Let me also add that, these computations, there are certain other links that are not torus links, which can be computed using these ideas. I won't talk about that today, but there are there are other links that can be computed this way. I hope somebody out there in the audience will find other applications to this technique. Okay, so in order to get started, we need some description of torus links as the closure of some braids. And so as is well known, there's this braid presentation of the MN torus link. You draw M points on the bottom of a cylinder and N points on the side of a cylinder, connect up dots in this way, and you get that braid description of the torus link. For us, it'll be advantageous to rewrite this braid closure in the following way. So we want to connect this dot to this dot. We can do so around the back of the cylinder, but up to isotopy, you can also connect them kind of the long way around. Anyway, in doing so, results in this picture, which if you turn your head sideways, you can see is like at a 45-degree angle, you can see is the closure of this fat crossing between M parallel strands and N parallel strands. Okay, So we can describe, so the usual way of describing the MN torus link as a braid closure is as the closure of this strand of this braid on M strands. We prefer this description as the closure of a braid on M plus N strands. One reason this is nice is because it makes the symmetry between M and N obvious. Okay. In order to use the technique from last time, what we'll do is we'll extend this family of braids to a family of braids decorated with symmetrizers. And we'll simplify that entire family of diagrams. Well, each one of those diagrams is going to represent a complex, and we'll simplify this entire family of complexes kind of simultaneously using the relations from the previous lecture. Those relations, by the way, to remind you, are here. So we have the braid-like, Reidemeister moves. If we see a strand with no symmetrizer on it, then we can introduce a symmetrizer at the expense of this kind of multiple, which you should be interpreted as a geometric series and a direct sum, and then some differential connecting the terms of that big sum. Then we have the recursion, braid absorption, and then the Markov move. Okay, so that's the basic idea. Introduce a big family of diagrams. Those diagrams are going to represent some chain complexes, and then we'll simplify all of those chain complexes using these relations kind of simultaneously. So this will be a big recursive computation, and the intermediate steps of the recursion are going to be not braids, but some kind of intermediate guys which have these symmetrizing complexes in there. All right. So the family of complexes, or rather diagrams, that we think about is written here. So this family of diagrams is going to be indexed by pairs of binary sequences, V and W, with the restriction that the V and W have the same number of ones. So we'll use the absolute value symbol to mean the number of ones in a binary sequence. And the diagrams that we define are, so I'll define it in an example, as in this example. So the relevant things to know are, so we have the parameter M, which is the number of zeros in the binary sequence W. Parameter N is the number of zeros in the sequence V. And the parameter L is the number of ones in V and W. So these red strands, these L strands, are exactly the strands which are sort of connected to a symmetrizer. And the binary sequences V and W describe how those red strands get shuffled in with the others. Okay, so for example, I'll zoom in here. So for example, this 0 indicates that the strand attached to that 0 avoids the symmetrizer and continues all the way down to the bottom left. I'll color such strands blue. Okay, so we have a 1 which connects to the symmetrizer, a 0 which avoids the symmetrizer, and so on. And all of the crossings involved in this process are positive. So this is just a positive braid together with a symmetrizer somewhere. Okay. And W describes how the L red strands, the symmetrized strands, get sort of shuffled in with the green strands. So this 1 represents a strand that hits the symmetrizer, and so on. This 0 represents a green strand that does not hit the symmetrizer. Okay. So I hope that's pretty self-explanatory. And as a special case, we see that if M and N have no ones, then the resulting complex has no symmetrizer, and we get just the braid that represents the MN torus link. So this guy appears as a special case. All right, to get ourselves started, we'd like to be able to kind of use the recursion for these symmetrizing complexes, but to get started, we need to have a symmetrizer somewhere. So the sort of 0th step is to start with the complex representing the torus link. That is to say, a diagram that has no symmetrizer, and we need to introduce a symmetrizer, like place a symmetrizer somewhere. First, let me just kind of point out that um, we'll be taking closures of these diagrams. That is to say, we want to take the Hochschild cohomology of these complexes of bimodules, whatever that means. But our big diagrams, it's gonna get tiresome to write big hats everywhere. So I will just not indicate the braid closure in any of my diagrams. The understanding, though, is that each one of these diagrams should really be closed in the plane. Like I really want to take the braid closure of everything. But I'll stop drawing that. I'll stop indicating that in my diagram. Okay, the first thing that I want to do is kind of single out a pair of strands here. So the rightmost blue strand and the rightmost green strand, I'm going to color them red. And because I'm taking the braid closure, I have a place where I can do Reidemeister 1. So I, oops. So I simplify using the Reidemeister 1 invariance, which if you remember involves no additional shift. And the result is this complex. Then I introduce a symmetrizer here, and the result is this expression. So it's a big infinite direct sum of copies of this diagram with some additional differential. And so the net result is the following simplification. If you start with if both binary sequences have no ones in them, then up to homotopy equivalence, you can replace it with this guy. So the initial zeros have both become ones. You have infinite many copies of that complex and some extra differential internal to that. For the actual computation now, so I want to compute the homologies of all these complexes represented by these diagrams, and we'll do it by basically reading these sequences from right to left. So there's 4 possibilities depending on whether these sequences end in a 0 or 1. And what we'll do is we'll deal with this one. We'll deal with this guy first. This will actually be the most complicated one. The others will be much easier. So first off, oops, ignore this. So first off, if both binary sequences end in a 0, then the relevant diagram looks something like this. So I've color-coded things. I have the blue strands and the red strands like blue, green, and red strands like usual. But I'm kind of singling out the last digit here, so the 0 on the right. So the strands which are sort of attached to those zeros, I'll kind of label them yellow. So notice if you just focus on the yellow thing here, there's kind of an opportunity to use Reidemeister 1, except that projector is kind of in the way. So the first step will be to move the projector out of the way. This isotopy of diagrams is a valid homotopy equivalence of complexes. So you move the projector out of the way, now you have a Reidemeister 1, and the result is this complex on the far right. Now you have a place where you can do the recursion. You see this yellow strand links the projector, links the little symmetrizer guy. Anyway, and so the recursion results in a direct sum of things, direct sum of 2 terms. The first term is, wait for the video to upload. Come on now. Or update, I should say. Okay, the first term is this complex, which you see is just exactly one of these CVWs. The second term, so this yellow strand, which previously had linked with this symmetrizer, is now unlinked, and we can rewrite this as follows. So after an isotopy, a bunch of Reidemeister 3s, we get this complex, and then, I altered my diagram. So after darn it. Anyway, after the inverse Reidemeister 1, we get this diagram, and it's easier to see if we if we color these things blue and green like they're supposed to be. This is exactly this CVW complex. All right, so the net result of what we just did is this direct sum of two terms with an extra differential and some shifts. So basically the zeros at the far right cycle around to the beginning and either both become a 1 or both become a 0. The next possibility is when one of the binary sequences ends in a 1 and the other ends in a 0. So the picture for this is something like what I've drawn here. Again, we'll single out the strands that hit the 0 and the 1 on the far right. We'll color them yellow. Once again, we move the projector out of the way with an isotopy, and then we apply right emitter 1 on the yellow strand, and the result is this complex. The symmetrizer absorbs these crossings that hit it, and the result of that is drawn here. And our yellow strand we now draw as a red strand because it hits the symmetrizer. And the resulting complex is just, again, one of these CVWs. The result is that the 0 so this 0 disappeared, and this 1 cycled around to the beginning. So that's what's written here. So this complex, so you have this homotypic equivalence. The other homotypic equivalence is essentially the same thing. It follows by symmetry. Okay, the final possibility is what if both binary sequences end in a 1? So this is in fact the simplest of all. If both binary sequences end in a 1, then the relevant diagram is something like this. And just a single application of that Markov move for symmetrizers yields this homotypic equivalence, and we're done. So this is a CVW. This is the complex CVW, where all we did was we delete. So we started with a complex CV1 W1, and then the ones just disappeared. Okay, up to an overall factor. So this is all summarized in this bullet in this list here. Okay. So in our 4 possibilities, we have these 4 possible simplifications, and one thing to notice is that each of these, the last 3 guys, they all actually simplify the pair of binary sequences. So each one of these decreases the length of either V or W. Decreases the length of either the first argument or the second argument. And so it, certainly simplifies. The left-hand side has been simplified during an application of these equivalences. This first bullet point, so the terms appearing on the right-hand side are not, they have the same length as they used to have, but I claim that they're actually simpler in a certain sense. So for example, sorry about that. For example, this term has more 1s in it. And we like 1s because a 1 presents an opportunity to use one of these relations at some points in the future. So in some sense, we've simplified it. So this term is in some sense simpler than the one we started with because it has more 1s. And in another sense, this term is simpler than the one we started with because, well, I guess we've decreased the number of zeros that occur to the right of 1s. So whatever 1s were present in this complex are now closer to the right edge of the complex, of this sort of sequence. And so in another sense, we're again closer to being able to use one of these relations. So in a certain sense, as long as the complexes we started with were not the all zeros, as long as the complex we started with was not one of these sort of all zeros guys, an application of these 4 moves will simplify our complex. And so this is what the computation looks like. You start somewhere and you apply a sequence of these moves, and the process terminates when you can no longer the process terminates when you can no longer use one of these relations. So it terminates here. Either V is the empty sequence, in which case W must be nothing but zeros, or W is the empty sequence, and V, again, is forced to have nothing but zeros. Remember, the number of ones occurring in V is supposed to be equal to the number of ones occurring in W, so if one of them is empty, the other one is just all zeros. And in either case, the complexes corresponding to that pair of binary sequences is just the complex of the unlink. So you have no symmetrizer, and you just have an unlink with, say, n components, n or m, depending on. Okay, so this is what the recursive computation looks like. Again, we have these potentially mysterious differentials to worry about. We'll see how to take care of those in a moment. So this is encapsulated in the following theorem. So we define a bunch of polynomials, which is sort of satisfies the same recursion as in the previous 4 bullet points. They're not quite polynomials because they may have these denominators of the form 1 over 1 minus q squared. But so the claim is, first off, there's a unique family of polynomials satisfying these recursions, and then the base case would be, so if V is empty and W is a sequence of zeros, then this polynomial is supposed to be the graded dimension of the homology of the unlink with so many components, which in these conventions is that guy. And I suppose I should also mention that it could be the other way around. W could be empty and V could be non-empty, but by symmetry, it's enough to consider one or the other. Anyway, so there's a unique family of polynomials satisfying this base case and these kind of recursive properties. Furthermore, that family of polynomials appears as the graded dimensions of these vector spaces. So this complex that we started with is homology equivalent to some complex whose underlying vector space is just so many copies of C. So the graded dimension is this polynomial from above. And the thing to observe is that the only powers of t that appear anywhere are even. So this is t squared, and this is t to the minus 2. So whatever this vector space is, it's supported in even cohomological degrees, and so the differential is 0 for degree reasons. So we picked up some mysterious differentials each time we applied the recursion, like each time we applied this step. But at the end of the day, we don't really care what those differentials were, because we arrive at a complex with 0 differential for degree reasons. So this miracle is basically, this is the computation. So we arrive at a complex with 0 differential, so that's the homology. Okay. So let me just conclude. So that's all I have to say about torus links, but I just want to conclude with just a brief comment on like how this could be applied in general. So by applying these relations in general, you arrive at some vector space with some differential. Even when, like this was, it's a little overly optimistic to expect that the Khovanov-Rozansky homology of your link, like suppose you want to compute the Khovanov-Rozansky homology of some link, it's a little overly optimistic to expect that it'll be supported in even degrees. So such an argument may fail, but still, let me just say sort of vaguely, the usual spectral sequence arguments apply here. So basically what's being computed here is like the E2 page of some spectral sequence, and then the higher pages can be computed either by careful determination of these differentials along the way, or by usual techniques, like you can compute the E2 page in 2 different ways and compare Okay, I don't want to say any more about that. But in the end of the day, um, we have the main computation. So the Khovanov-Rozansky homology of the MN torus link. That's the homology of this special case of what we just computed. And there we go. Okay, thank you.